Okay, we're going to continue on, and we got into some organic here. And last time we got into alkanes, and alkanes are kind of the simplest organic compounds you could have. They have really kind of the carbon-carbon single bond as like their functional group. They're all single bonded. They have a general formula of CnH2n plus 2. And as we talked about, really those first 10 alkanes, sort of names and formulas are really important to learn as they are really the basis for everything else that we deal with in here in terms of names. So all other organic sort of names do come back to those. So again, like we saw, CH4 is methane. 2 carbons, 2 times 2 is 4 plus 2 would be 6 hydrogens. That's going to be ethane. C3H8 will be propane, and so forth. So all of these do end in ANE, just like sort of the organic sort of group name there. And obviously we have butane, pentane, hexane, heptane, octane, nonane, and decane for all these guys. We have formulas that we talked about, and there's a couple different types of formulas. There's the expanded sort of formula, and then again in the expanded structural formula, we do just basically draw everything out like Lewis structures, basically. So this is our expanded structural formula. We also have a condensed formula where we really just don't draw out the hydrogens. So something like this would be a carbon with 3 hydrogens. Next to it would be a carbon with 2 hydrogens. And lastly, a carbon with 3 hydrogens at the end there. And again, that is what is known as the condensed formula. We also have the line formula, which is pretty much just lines. And again, as we talked about, pretty much at the end of each of those lines or anywhere 2 lines sort of come together or multiple lines come together. Thank you. Those are carbons. So this would be our line structure. Yeah. And obviously, we also have just our regular sort of molecular formula where we have up there C3H8 is our molecular formula. Now we have compounds, especially alkanes and so forth, which are straight chain. And something like this is a straight chain where it just kind of goes straight across. There's nothing branching off. We also have some which are branch chains where you do end up getting, some branching occurring along the way here. And that's sometimes referred to as branch chain. And we also have cyclic alkanes, and that's where they basically will kind of put their ends together there and make sort of a structure here. So this is a cycloalkane. Cycloalkanes are just like the regular alkanes, except you put cyclo in front of it. And will have 2 less hydrogens because the carbons basically come together, and that means that you have to lose 2 hydrogens to do that. So instead of like everybody above there, this guy actually only has 2 hydrogens at each spot there where there's carbons. Thank you. And that would give us C3H6 in this case. Again, it loses 2 hydrogens when it kind of closes up on itself. We talked about naming, and when we name alkanes, we typically go by the IUPAC way of naming, International Union of Pure and Applied Chemistry. And really with this, we always want to find the longest carbon chain. We then want to find the groups that are attached. And remember that if these groups are basically carbon-based groups, they are sometimes referred to as alkyl groups, YL. And what makes something an alkyl group is it basically is the same thing as the alkane, but it has one less hydrogen, and having that one less hydrogen allows it to connect into the chain as well. So here, again, instead of methane like this, where it is already has a full octet with the carbon, if we take one of those hydrogens off, and now has a spot where it can connect into that longest carbon chain. Again, this is methane, which is an alkane. With one hydrogen missing, it is named with a YL at the end, and this is known as a methyl group. So again, these alkyl groups are really just the same as those alkanes, just missing a hydrogen to give it a place to connect into the main chain without having too many, obviously, bonds to that carbon, which we never want more than 4 bonds. We also have halogens, which are groups, so they're named fluoro, chloral, bromo, iodo as well. Once we do that, really our longest carbon chain is going to be kind of the base of our name. And it will probably match one of those alkanes names. We have our groups. And then the next thing we want to do is number the longest carbon chain. And we want to give, in this case, the groups attached the smallest numbers. So usually you'll have 2 ways at which you can number that longest carbon chain. You want to go whichever way has the lowest set of numbers for those groups attached. And then we basically put everything together. We go groups in alphabetical order. Regardless of any prefixes. So remember as well, if we have more than one group within the molecule, we could use prefixes like di for 2, say, methyl groups, or tri if there's 3 methyl groups within there. We do want to always, when we kind of write it as well, we typically will always go between a number and a letter. We do a dash. Also, if you're going between a letter to a number, we also do a dash. And if you have 2 numbers, we separate it by a comma. And you do have to give the location. That's pretty much what the name is all about. It's all about basically location, 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 basically telling everybody where you can find all these groups on the longest carbon chain. We also talked about isomers. And remember that isomers have the same molecular formula, but a different connectivity. So they have the same sort of molecular formula, but different connectivity. And because of that, they are different compounds, and they will have different names. As we did, I think, at the very end last time. That's a really good way to know, for example, if you actually did draw different isomers rather than just it looks different, is to name everything. If you end up with different names, and obviously you named it correctly, you should have different compounds and they are isomers for each other. If you end up with the same name, you pretty much, even though they may look different, pretty much drew the same thing. So that's a really good way to kind of do that. Any questions? Hold on. So again, just a reminder, we've got maybe something like so why don't you give the name for that? Why don't you give the name for this guy? It's 2 H's. Okay, let's take a look here. So again, we want to go longest carbon chain. So on the first one, that's 1, 2, 3, 4. You could really get 5 either coming down or you could go up. In that case, you really have 2 options for 5. So I'm just going to take this straight one there And that does look like 5. So we do know that the base of our name here should be pentane, as that is 5 carbons, all single bonded here. As again, there is a carbon there, 2, 3, 4, and 5. And that means we have a couple of groups hanging off of there. So we definitely got a group right there. And we do got a group hanging off of here. Once again, in line structure, if there's just a line and nothing at the end of it, it is a carbon with the appropriate amount of hydrogens. And that would make this a methyl group, as there again should be basically a carbon with 3 hydrogens at the end of that line. Here, there's actually something written, which is a halogen. So that would be a bromol group, as that's again how we name our halogens: bromo, fluoro, chloral, and so forth. At this point, we do want a number. So going left to right here, we will go 1, 2, 3, 4, 5. So that gives groups at carbon number 2 and carbon number 4. Heading in the other direction, I'll go orange here. 1, 2, 3, 4, and 5. That also gives groups in terms of 2 and 4. So in this particular case, it is a tie in the sense of no matter which way you go, you're going to end up with the same number. So what we want to then look at next is, since number is not going to separate them, the next important thing is putting our groups in alphabetical order. So in this particular case, the B would come first versus the M. So because of that, sort of the next priority thing, we actually would want to go in this direction. That's going to give our bromine there the alphabetical kind of smaller number, since we could do that, and it's a tie in either direction. So again, if there happens to be a tie like this, you want to kind of go to the next important thing in this case, which is alphabetical. Try to give the one with the alphabetical sort of priority the smaller number. So doing so, that would mean that we would then have a 2-bromol and a 4-methyl. And that's everything that we need to name this. So this will be a 2-bromol dash 4-methyl. Stick it together there, and pentane in this case. Any questions on that there? All right, looking at the next one, what we got here. Longest carbon chain is how many? So we got 5. Any larger than that? Let's see. Well, if I go straight across, I got 1, 2, 3, 4. So let's go straight across 1, 2, 3, and then go down 4, 5. That's pretty good. Any others? How about if I went 1, 2, 3, 4, 5, and 6? Thank you for the sound effect. I like that, by the way. That's good. So again, you do want to make sure that you check all the ways, right? There could be one hiding there, which it looks like it is. Also want to keep in mind right at the end, there is not a carbon, that's a chlorine. So sometimes people see the C and just count it as a carbon at the end there. So looks like actually 6 is going to be our winner in this case. And that means we do got some groups in this case. So we'll start with the 6. 6 is going to be hexane, right? So that's going to be hexane as the base of our name. We now got several groups hanging out here, I think. So we got, once again, not a carbon at the end, but it is a chlorine. So that would be a group. We definitely got a methyl group there and a methyl group hanging out there. So we have, in terms of our groups, this is going to be a chloral group. That obviously is going to be a methyl group, and that is going to be a methyl group. And since we actually do have 2 methyl groups within the entire molecule, those 2 guys are going to become a dimethyl group again, because there's more than one of the same group within there. And now we need to do the naming. You could probably see that really you could go both ways, but since we have that chlorine hanging off there at the very top, that's going to definitely give us a smaller number if we number in this direction: 1, 2, 3, 4, 5, and 6. Obviously, if we started at this direction, we're not going to hit a group until carbon 3. So we definitely want to go kind of the top way down. That means that's going to be a 1 chloral, right? And then over here at 3 and 4, we have our dimethyl. Remember, we need a comma between those two numbers, and we do have to give both of them. And again, a reminder, even if they're on the same carbon, you have to give the number twice. Yeah, so even if it's the same number, you have to give twice. So that's everybody. We're going to go alphabetical order. In this case, remember, we're looking at the C versus the M. We don't look at the prefix here. So the di is sort of ignored. And putting all that together, that's going to give us a 1 chloral 3,4 dimethyl hexane. Questions on that one. So a couple of reminders. Again, make sure you do kind of check all your options on the carbons. Once again, not always going to be the straightest sort of drawn one. And again, alphabetical there, regardless of the prefix. And any questions on either of those two there? All right, so let's take a look at another sort of approach here that we want to do. Let's just do something here. Let's see. Whoops. All right, let's take a look at this. If we had we'll do 2 ethyl, do 3 methyl. That's what I was gonna do. 3 methyl. And we'll do hexane. Why not? We'll do that one. All right, let's say we wanted to actually draw this. So we have the name and we want to draw it. We've done obviously some formulas and given the names. So if we have the name and we want to draw it, I might have mentioned this last time, but I personally think this is probably the easiest of everything, is because it kind of tells you what to draw. So whenever you have a name and you want to actually draw it, you should always work backwards in the name. So when you have the name and you want to draw it, you should always be kind of going in that direction to sort of handle it. Why should we do that? Well, we do know that the last part of the name tells us basically how many carbons our picture should have, right? So we want to kind of start at the last part of the name and work our way across. So when I see hexane and I see the ANE and I see the hex part of it, that tells me I have 6 carbons, and the ANE tells me they're all single bonded. So that's exactly where you should start, with nothing more than just the 6 carbons. So let's say we're going to do our condensed formula. So we would just start with 6 carbons, 1, 2, 3, 4, 5, and 6, basically. All right, so frankly, that takes care of this part of the name, right? So we're working our way through. Now, what we have left are our groups, right? So 2 ethyl, 3 methyl, and those are basically the groups that are attached to these 6 carbons. And the numbers is where they are attached. And the good news is, since you are drawing it, you have the option as to either over here is carbon number 1, or if you wanted to, you could call that carbon number 1. It is your choice since you're drawing it. I'm going to actually start with carbon number 1 on the left, but once again, if you wanted to start on the right there, you could. But I'm just going to call my carbon number 1 there on the left. Now, by the way, once you decide that, you have to kind of stick with it. You can't just go back and forth. So if that's my carbon number 1, basically what I know is at carbon number 3, I should find a methyl group. So I go to carbon number 3, which is right about here. I also know a methyl group is based off of methane, which is 1 carbon. So just a carbon, right? That takes care of that. I then will come here, and that means at carbon number 2, there's an ethyl group. Ethyl is based off of ethane, which is 2 carbons. So at carbon number 2, I can lay myself up a couple of carbons. At this point, I've scratched out my entire name, and I have nothing else to draw. Everything else here is hydrogen, right? And what we talked about was carbon should always have 4 bonds. So You're going to count up how many hydrogens you need to get carbon-4 bonds. So the guy at the very end here on the right has one line coming in, which means it would need 3 hydrogens. The guy next to it has 2 lines coming in, which means to get the 4, it needs 2 hydrogens. Next one also has 2 lines coming in, which means to get the 4, it would need 2. Guy coming next has 3 lines, which means it just needs 1 hydrogen to get to 4. Guy next to him has 3 lines, which means it needs 1 hydrogen to get the 4. Guy at the end has 1 line, just needs 3 hydrogens to get there. Now, I could have filled in my hydrogens with my groups when I drew it, but just in case you couldn't remember, you could also do it for the groups. I see the ethyl here at the end has 1 line, which means it needs 3. I see the ethyl here next door has 2 lines, which means it needs 2. And obviously my carbon up here has 1 line, which means it needs 3. And there it is, yeah. So just like that. So I would start with the carbons. I would put your groups in. It's up to you on the groups. You want to put the hydrogens in with the groups, or you want to do it like this, it works too. And then obviously everybody gets the appropriate number of hydrogens, again, to get yourself to 4 bonds. Any questions on that there? Yeah. So carbon always makes 4 bonds in this thing. It should never have more. It should pretty much never have less. 4 is the magic number for carbon. Yeah. And basically, if you have nothing else to put on your picture, the only other thing you put there would be hydrogen. So the appropriate number of hydrogens to get them to 4. And just like normal hydrogen, obviously, you should only have 1 line, right? And 1 bond, 2 electrons. Now, if you were going to do something, say, like a line structure, I would approach it the same way. I would start with my 6 carbons, right? 1, 2, 3, 4, 5, and 6. And do the same thing. So again, if I call that number 1 over there, I would just go to carbon number 3, which would be down here, and a methyl group would be just a line, right? Again, nothing at the end of it. And at carbon number 2 would be an ethyl group, which should have 2 carbons, 1 and 2, and it would look something like this. Yeah. So the nice thing about the line structure, you don't have to go in and put the hydrogens in, so you just got to put the lines and stuff like that. So again, always work backwards with the name is the best approach. Start with just the basic carbons, fill in all the groups, and then finish with the hydrogens. And obviously, if you're going to do some type of expanded one, the only difference is on the top one, they're just going to draw bonds to all the hydrogens, right? And that's going to be the expanded one in that case. Any questions on that there? All right, so why don't you try some here? Maybe want to just make up some here and see. I don't know. Let's do 2 bromo, 3 propyl. Let's do we'll do pentane. I think that'll work. Let's do 2, 3 dimethyl heptane. Let us do chloral cyclopropane. And let's do 1 bromol, 3 methyl cyclobutane. All right, so take a moment and draw. You can do condensed if you like, structures for each of these. So again, work your way backwards on these. Okay, let's take a look, see how we're doing. So once again, we have the name. Always want to work backwards. So we'll start with the first one here, which is pentane. So that is going to be 5 carbons. So 1, 2, 3, 4, and 5. And at this point, that will take care of this part. Once again, you could choose whichever carbon you want at the end there to be carbon number 1. I'm going to choose this one here to be carbon number 1. So that means for me, carbon number 3 is right here. And at carbon number 3, there is a propyl group, which is based off of propane, and that is 3 carbons. So I'm going to put 3 carbons up there as part of my group. That'll take care of that. And since this again the carbon number 1 for me, carbon number 2 would be here, and at carbon number 2 there's a bromine there, and that would take care of that. Again, I'm out of name at this point, so we're just going to kind of fill in with hydrogens. Again, the goal here is to get carbon to 4 bonds. So this guy has 1 coming in, which means it needs 3. This carbon next to it, yeah. Yeah, so sometimes when you have the name and you draw it, it will actually end up being a different name, if that's your question. Yeah, yeah. So that happens a lot sometimes, yeah. Especially when they just make up names to do it. But yeah, so in this situation, you definitely obviously would just want to draw it based off his name. But if you were given the structure, you would obviously name it something different. Yeah. Other questions? So coming here, this has 3, which means you'll end up with 1. This guy also has 3, which means you need 1 hydrogen. The one next to it has 2 lines coming in, which means it needs 2. The guy at the end here has 1, which needs 3. I'll try to squeeze it in there. CH3 there at the end. And once again, we could kind of come up to our groups and do the same thing. This has 1 line, which would need 3. This has 2 lines, which would need 2. And this also has 2 lines, which would need 2 as well. Obviously, the bromine needs nothing, obviously, because it's not carbon. Again, if you were going to do some type of line structure, you would kind of work it the same way. We'd go 1, 2, 3, 4, and 5. And again, I'm going to call this carbon number 1 for me. So at carbon number 2, I could put my line, and I do need to put the bromine, otherwise it's a methyl group. And at carbon number 3 here, we'll go a propyl group, so up, down. So again, 1, 2, and 3 sort of attached there. And it looks something like that there. Questions on there? All right. And as was mentioned, definitely if we were to have this for the formula, we would name it something different than the name that was given to us. Yeah. All right, so taking a look at this one here, heptane, I'm not liking it already. That is 7 carbons. So 1, 2, 3, 4, 5, 6, and 7. That takes care of that. 2,3 dimethyl. So the dimethyl means that there are 2 methyl groups, and they are located at carbon 2 and carbon 3 here. So they are not on the same carbon. So once again, I'm going to call this my carbon number 1. So for me, carbon number 2 would be right next door, and we would put a methyl group there. And at carbon number 3, we could put a methyl group. And again, that is our dimethyl at those 2 locations. Now we're just going to fill in hydrogens basically for everybody else. So we need 3 here because he has 1 line. 2 lines means 2 hydrogens. 2 lines means 2 hydrogens. 2 lines means 2 hydrogens. This one has 3 lines, so 1. This has 3 lines, so 1. And this guy at the end has 1 line, which would give us our 3 hydrogens. Same thing if you're going to line structure this guy up, you're just going to start with these 7. So 1, 2, 3, 4, 5, 6, and 7. Again, coming to carbon number 2, we'd put a line, and carbon number 3 would put a line, and that would be our line structure for it. Any questions on either of those 2 there? All right, so coming backwards here, we have cyclopropane. So the cyclo part of it tells us it's a ring, right? And the propane tells us it's 3 carbons. So again, a lot of times people will roll with just the line structures on those cycloalkanes like we talked about. So basically a triangle in this case. And since that takes care of that chloral means there's a chlorine on it, and you just put a chlorine. You could put the chlorine on any of the corners there, because wherever that chlorine is, it's assumed to be carbon number 1. This is what is sometimes referred to as being monosubstituted, since there's just one group on it. And in a case like that, you don't have to give the number of where it's located, because again, it's assumed to be carbon number 1. So this is the only thing attached. So wherever it's located would be carbon number 1. Now, if you wanted to do more of a condensed for this, you would do it the same way. You would just kind of put your carbons in, basically. And in this case, again, I'm going to put my chlorine up here. And at this point, I could put my hydrogens. So this has 3 lines coming in, so it just needs 1. This has 2 lines coming in, needs 2. And this guy has 2, it would need 2 as well. So that'd be more the condensed formula for like a cycloalkane. Yeah. Any questions on that there? Lastly, here we got cyclobutane. So cyclo, again, going to tell us it's a ring structure. Butane is based off of 4 carbons. So that's kind of like the square move there. And once again, you could pick any of those corners as carbon number 1. In this case, though, we don't have just one group attached. We do have 2 groups attached. And when you do have 2 groups attached to a cycloalkane, you do have to give numbers. So in this case, what you would want to do is probably give alphabetical kind of the priority there, give it the smaller number. And since it is 1 bromol, once again, I could put that bromine on any of the corners. So I'm just going to put it here. And because I put it there, for sure, that's going to be carbon number 1. And you could go clockwise, or you could even go counterclockwise in this case. You will actually end up at the same spot, but we'll go 1, 2, 3 here, and we will have a methyl, which will look something like this. And again, if you wanted to do more of a condensed type of deal, you could, again, just kind of put your carbons in your corners and attach your bromine, and also attach your methyl here. And then just fill in your hydrogens, which we need 1 there, 2 there, and 1 there. Yeah, and kind of fill it in as well. Any questions on drawing these? So again, I think these are sort of the easiest ones to kind of do, because it kind of tells you what to draw. As long as you kind of work your way backwards, you can kind of put the structure together fairly straightforward, hopefully. Yeah. Any questions on that there? Okay, so let's take a look. So it looks like probably just straight across here is going to do us here. 1, 2, 3, 4, 5. Kind of really your only other option would have been like 1, 2, 3, and then down, which will give you 4. And obviously the same thing this way. 1, 2, 3, 4. Obviously is less than 5. So 5 here is going to be pentane as the base of the name. That leaves us a group right there, which is a chlorine, and a 1 carbon group right there, which is our methyl group and our chloral group. And again, we now want to number the longest carbon chain, and you can probably just visually see if you go left to right here, it's probably going to be a winner. 1, 2, 3, 4, 5. Obviously, if you went in this direction, you're not going to hit the first group until carbon number 3, which is obviously larger, and you would not want to go in that direction. So because of that there, we do have a 2 chloral and a 3 methyl. Again, alphabetical C before M would give us 2 chloral dash 3 methyl, and then slap a little pentane at the end of it there. There it is. Any questions on that name there? Okay. So hopefully you can kind of see naming. It's just about sort of giving locations where you can find all these sort of parts, if you will, along the longest carbon chain. And that's sort of how you should approach naming. It's just kind of breaking it down, take all the small things, put them together. Obviously, as we talked about here with a monosubstituted cycloalkane, again, we're just going to give the group name in front of the cycloalkane. So obviously our longest carbon chain is this 6-member alkane, which is based off of hexane. And because it is a ring structure, that is where we get our cyclohexane. And what we have here is our 2-member carbon ethyl group that's hanging off of it. And once again, that is ethyl cyclohexane. Once again, you do not need to give the number. It is assumed to be carbon number one. And that's because, frankly, if you drew it like this would also be ethyl cyclohexane. It's just turned around, basically. Just kind of turn the thing around, and it's the same location where that will be. All right, so we kind of talked about drawing. Again, working backwards is always a good approach and do there. So why don't you draw this one, the condensed and line structure for 3-bromo, 1-chloral butane. Okay, so let's take a look. Again, we're going to work backwards, always with the name. So butane tells us we should definitely start with 4 carbons, which is what butane is. That takes care of that part. Again, you could identify left or right as carbon number one. So I am again going to go kind of left here is my carbon number one. And that means that carbon number one, I actually do have a chlorine. So we're going to put a Cl there. And then at carbon number 3, which should be right around here, I have a bromine. Once again, I'm kind of out of name at this point, so it's just hydrogens now to get everybody to 4. So we'll need 3 there. This carbon's got 3 bonds, which needs 1 hydrogen. 2 bonds needs 2 hydrogens. And this guy here would be 2 there for our guy. That would be obviously our condensed formula. Our line formula would be same start. We're just going to go 4, kind of up, down, and up. Once again, I'm going to start with this as being my carbon number 1. So that means really here I do have a chlorine hanging off of that very first one. And that would mean at carbon number 3, I do have a bromine. Once again, we do need to write the Cl and Br. Otherwise, if you leave it empty, then it's a methyl group, right? Which is not what you're trying to do. Any questions on it? Yeah. Expanded is pretty much just like the condensed, other than you just kind of draw out the hydrogens basically on everything that has hydrogen. So this would be technically your expanded formula here. Looks something like this. And you basically just draw out the hydrogens. So yeah. Yeah. In terms of are you talking about like the chlorine or the bromine? Technically no, but I would say most people kind of go with like kind of the peak or the trough as to where you would kind of put the line. So very rarely would you probably see somebody kind of draw the group like down like that rather than they would most likely kind of go with the peak, if that makes sense. Which is why I kind of went down here. At the end, you do have an option. You could actually go either way. I probably want to go straight because it is going to kind of get confusing. So you'll kind of ruin the. So if you kind of went straight at the end there, what you're going to probably do is now take out the carbon that should be there, right? And so you definitely don't want to go straight, but up or down at the ends, it's okay. In terms of also for the condensed, it doesn't matter either. So if you like, I put all the chlorines and bromines up on top, you could drop them on the bottom as well. It doesn't matter. And that's really because you have a lot of freedom on that because they're all single bonds. So because they're all single bonded carbons, they actually can freely rotate at 360 degrees around. So technically they could be anywhere you want, up or down in situations. Other questions? Okay, we're going to continue on here. So why don't we try one more here before we kind of move on from this? Why don't you give this guy a name and see what you come up with? 7. Anybody else? 7, 8. All right. So let's see. So we got straight across 1, 2, 3, 4, 5, 6. Not too bad. All right. We got maybe 1, 2, 3, 4, 5, 6, 7 going that way. We also have let's see here. We got 7 beats 6. We got 1, 2, 3, 4, 5, 6, 7. So that's 7. That's pretty good. And we end up with 1, 2, 3, 4, 5, 6, 7, and 8. Yeah, so 8 looks like a winner here. So again, like I mentioned before, a good reminder, make sure you do check sort of all your options. So we do have 8 here, which means the base of this name is going to be octane. We have a 2 carbon group hanging off over here, which should be a ethyl group. We got our 1 carbon group hanging off over here, which will be our methyl group. You could maybe see it, but again, if you kind of number over here, starting with 1, 2, 3, 4, 5, 6, 7, and 8, that will give us groups at 3 and 5 here. There it is, 5. If we go in the other direction, 1, 2, 3, 4, 5, 6, 7, and 8, we will end up with groups at 4 and 6, which is larger, right? So we would actually want a number in this direction here, as that's going to give our groups the smaller numbers. Now we want to put it together here alphabetically. So 5-ethyl first, regardless that the number is larger, doesn't matter. -3-methyl, and a little octane at the end of it. Yeah. Question on that name. Yeah. It doesn't matter. So alphabetical takes the priority there. So you can have alphabetical, but the guy will actually have maybe a larger number and stuff like that. So that does take priority. Yeah. Other questions? Now, like we saw in that earlier example, if you have an option of going either way and it's the same numbers, then that's why we kind of go to alphabetical as kind of the next option there to give it the smaller number. Question on naming or drawing these things. All right. So I think we'll skip those. We can do similar ones, I think. All right, let's finish up here, talk about alkanes, some properties which we've touched upon as well. Again, alkanes with 1 to 4 carbons are gases at room temperature. As we talked about at the very beginning, they are nonpolar, which means they're basically held together by those very weak dispersion forces. And it doesn't take a lot for them to kind of go into the gas phase. So methane, ethane, propane, butane will definitely be gases. Alkanes with 5 to 8 carbons are highly volatile liquids. And again, volatile means, again, it can go into the gas phase really, really easy. So even though it starts in the liquid phase, just opening the bottles enough for it to basically jump out into the gas phase and stuff like that. So as we talked about before, you do want to be careful when you're dealing with these because of that property, and they're also very flammable. I usually don't want open flame near any type of organic compound because that's not usually a great combination. 9 to 7 typically will have higher boiling points. So you'll actually start to see the boiling points of alkanes increase with more carbons. And that's because the strength of dispersion forces, even though they're really weak forces, actually increases with more carbons and more electrons. So more carbons means more atoms means more electrons. So it actually strengthens that weak sort of interaction. And again, as we'll talk about some other chapters, really long chains of carbon do make other things like waxes, which obviously are solids at room temperature. And again, things with like 25 or more carbons are very more sort of soluble or solid. Alkanes, again, nonpolar means they are going to be insoluble in water. Once again, as we talked about at the beginning as well, typically your organic layers, your top layer, your kind of water or aqueous layers, the bottom layer, if you mix an organic in and something in water. Flammable in air and found in crude oil. That's again how they make all those things. They basically, oil is just a giant long chain of carbons attached to carbons, and they break it up into smaller pieces like octane and gas and stuff like that, right? And they make different sort of properties. We're going to finish up talking here about alkanes and a couple of types of reactions that they undergo. One we've seen before when we were talking about types of reactions. And alkanes basically will undergo a combustion reaction. And these are sort of that organic combustion reaction that we talked about. So pretty much if you got an an alkane or an organic guy, and you add oxygen to it, your end result there is going to be CO2 and water. So this is sort of your organic combustion reaction. Do a little balancing like we're in chemistry class, maybe. There we go. Let's see how I did. But pretty much your three components of an organic combustion reaction is you have an organic compound that is reacting with oxygen, and on the other side, pretty much that's going to be your end result there, CO2 and water, unless you have an incomplete combustion, and that's give you carbon monoxide and water, but most of the time it's going to be CO2 and water. Also releases a lot of energy. That is pretty much what happens here when you open up the gas vent, right? Get the methane out, give it a little spark, you get fire, right? Combustion engines, right? Same idea, gas, air mixture, right? Combustion basically happens, provides a lot of energy to power your car. Here's butane. Again, same idea. You can see organic O2, CO2, and water. Pretty safe bet that that's going to be the end result that's going to happen there. Now, another type of reaction that actually alkanes undergo are what are known as substitution reactions. And in organic chemistry, there's a few different types of reactions. There's substitution reactions, there's addition reactions, and there's what's known as elimination reactions. And alkanes can, I'll think of it right here, alkanes can undergo a substitution reaction. And typically in a substitution reaction, what happens is, much like the name implies, one element gets substituted for another, basically. So one comes off and the other guy comes on to the spot. So for example, if you had like just a regular alkane here, and basically all those hydrogens here are pretty much equivalent. So any one of those hydrogens could basically be involved. And if you react with something like Br2, which is basically just two bromines together, and usually this involves some type of heat to be involved, or you'll sometimes see UV or light listed as a sort of necessary component for it. But basically, in the substitution reaction, what happens is one of these hydrogens comes off and one of these bromines go on in its place. And one of the things that you'll see as we go through these different chapters, when you need to draw the products, there's pretty much only one part of the molecule that changes. Everything else basically stays the same. So for example, I could pretty much copy identically everything over here except for the hydrogen I circled. So I could just, without even thinking, I could just copy it down exactly like it was on the other side. Now, the only thing that changes here is our hydrogen is going to come off, bromine's going to come on. And by the way, there's a second bromine there, right? And that's really Br minus. And that hydrogen that comes off is H plus. And those two guys could come together to make HBr, an ionic compound. And you'll make some HBr in this case, basically. So this is a substitution reaction. This is what is referred to as being monosubstituted, which means just one hydrogen comes off. And usually if you have to draw this, that's usually what you would draw. Under the right circumstances, you could kind of force all those hydrogens basically to pop off and kind of be replaced with some bromines or chlorines. You could also do this with chlorine, which is a halogen. So halogens are kind of what are used to do that. Chlorine, bromine is typically what we'll use. Occasionally iodine, but usually chlorine and bromine are the two main ones here. So if we take a look at this reaction, same idea. This is cyclohexane. It has two hydrogens at each of the carbons. And once again here, what's going to happen is this hydrogen is going to come off, and one of these bromines is going to basically take its place and come on. And once again, nothing else changes other than you pop the bromine up there. And you still have that same second hydrogen that was there originally. And once again, they're going to come together. The hydrogen came off with the bromine. So these are two types of reactions that alkanes undergo: combustion reactions and substitution reactions, and pretty much pop off a hydrogen, put on one of the halogens, and that is it in terms of those. Any questions out there? Yeah.
Hydrogen that comes off, is it off?
It is, yeah. So it basically comes off as H plus. This is also done in a it's sort of an environment, aqueous sort of environment where there's some water molecules and stuff like that. So it does come off kind of like an acid as H plus, basically. Other questions? Okay. All right, so that is alkanes. We're now going to talk about two other types of organic molecules, and these are alkenes and alkynes. Alkenes has a functional group of carbon-carbon double bonds. So you got one double bond. Alkynes are carbon-carbon triple bonds. So you got at least one triple bond happening there. As you can see here, this is an alkyne, triple bond here between the carbons. Remember, as we talked about, every time you put on a bond, you lose two hydrogens. So again, if we started with our single bonded alkane that has two carbons, once again, this is ethane. To put on our double bond, we would have to lose two hydrogens, one from each carbon. Basically these two. And as you might expect, as we might have touched upon before, they're actually named based on that ethane. But since it has a double bond, it's not ethane, A-N-E, it is ethene, E-N-E, like an alkene, E-N-E. So that is ethene. And if I need to throw a triple bond on, I'm going to take out two more hydrogens, and we'll actually end up over here to this guy. And we will now have ethine, Y-N-E, just like an alkyne. Yeah. So an alkane ends in A-N-E, and that's how you know it's everybody's single bonded. E-N-E means double bond at the end. Yep. Or a double bond somewhere in there, at least one. And Y-N-E means triple bond. And again, we do lose some hydrogens along the way as we continue to double bond or triple bond it out. Any questions on that? So once again, these are what are referred to as their functional groups. The carbon-carbon double bond and the carbon-carbon triple bond for our alkyne. So alkenes and alkynes are a family of hydrocarbons. These guys are unsaturated hydrocarbons. So if you remember when we talked about alkanes, they are saturated, which means each carbon has the maximum number of hydrogens that you could have. You lose that saturation once you add a double bond or a triple bond, as we just talked about. In order to make room for those, pretty much you got to get rid of some hydrogens. So those carbons will not have the maximum number of hydrogens that it should have. They do react with hydrogen gas to increase the number of hydrogen atoms and become alkanes. So as we will talk about, one of the reactions that alkenes can do is, for example, if you took an alkene and you added hydrogen to it, H2, I'll just write it underneath. This reaction is actually a reaction that's known as a addition reaction. And an addition reaction is different than a substitution reaction. In a substitution reaction, like we just talked about, somebody comes off and somebody goes in its place. In an addition reaction, we actually just throw both things onto it. Yeah, so both of those hydrogens end up getting thrown back on to those carbons. Now, if you think about kind of what happens when we put the bond on, we take a hydrogen off of each carbon. So the hydrogens don't come off of the same carbon. They come off of each carbon within the double bond and even the triple bond. So when we put the hydrogens back on, they actually go to each carbon separately. So one carbon will get a hydrogen, the other carbon will get a hydrogen. So what will end up happening in this case is this. I'll make these guys red, baby. Each of these hydrogens are going to end up at those carbons. Now, if I just put the hydrogens onto those carbons, do I have room to do that the way it is? I cannot, because then carbon will have like 5 bonds, right? And that's too many. So what always happens in this addition reaction with alkenes, regardless of what you are adding, you pretty much always need to make room for it. So the way we make room for it is we make the double bond into a single bond, and everything else remains exactly the same. So what you would do in this case, and we'll talk more about this a little bit later on, but you basically just copy exactly what you got, except make that double bond into a single bond. And what that is going to do is now make room for each of those hydrogens to be able to come on. And one's going to go to one carbon, and the other is going to go to the other carbon. And now we have room without going over our bonds, and we basically pop it back on. This is what is known as a hydrogenation reaction. And we go from an alkene to an alkane. Yeah, single bonded. So we go to becoming more saturated here, unsaturated to saturated in this case. So that is an important reaction that alkenes do. Basically, we add on two things to where the double bond's located. So that is always where those things get added onto, wherever the double bond's located. All you have to do is make it a single bond and put one on one and one on the other. Everything else in the molecule remains exactly the same. Nothing else changes. So you should just copy it exactly the same, double to single, put on your two things. Any questions on that there? All right, so identifying alkenes, they do have a general formula of CnH2n, and that is because they do lose those two hydrogens when we make the double bond. So instead of like an alkane where it's 2n plus 2, here we lose those extra two and they have two less. They're kind of very similar in terms of formula to the cycloalkanes. Because they come together, we lose those two hydrogens. Because we add the extra bond here, it does lose that. It also changes the bond angle. We now have here 1 electron pair, 2 electron pairs, 3 electron pairs. And we also have 3 bonds, 1 bond, 2 bonds, 3 bonds. And that's going to give us our trigonal planar geometry. And we actually see a 120 bond angle. These are not as zigzaggy in a sense as our 109.5. They're similar, but they don't have the exact same sort of bond angle as our alkanes do because of that double bond that is there. Again, they make basically that triangle shape there when they make that double bond happening. All right. So ethene is sometimes called ethylene, and it's an important plant hormone. When we look at alkynes, these again have the functional group of a triple bond. And they have a formula of CnH2n minus 2. So because they have 3 bonds, they lose 2 hydrogens when they make the double, and they lose 2 more when they make the triple. So here we're actually subtracting 2 to get the proper number of hydrogens. So as you can see here, 2 carbons means 2 times 2 is 4, minus 2 is 2 hydrogens here that is left over. This one actually ends up being a little bit different in terms of the geometry as well. It ends up being 1 electron pair, 2 electron pairs, and 2 bonds. That is our linear geometry. That is our bond angle of 180 degrees. Now, I will say sometimes in terms of line structures, you do see them drawn a little bit different. I will say that people will still sort of a lot of times do our double bonds, kind of the zigzag approach. But when it comes to triple bonds, you will sometimes see it kind of flatten out. And you won't see that because the geometry here is linear, right? So they kind of draw it like that. Now, that's really important when you look at that to make sure you don't miss any carbons. By the way, how many carbons does this have? What I just drew there. It has 1 carbon, 2 carbons, 3 carbons, and 4 carbons. Can't tell you how many people just breeze right by those two carbons there and just kind of look at the ones on the outside. So there are two carbons there. And again, sometimes it's missed by people when they see it in a line structure because it's kind of straightened out. So very commonly those carbons by the triple bond are sometimes missed. Yeah. Questions on that there? All right, so the first one is an alkene or an alkyne. First one is a alkene. It's got a double bond, like a triple bond, but missing one, right? The guy on the bottom is an alkyne, right? And that's got a triple bond action happening. By the way, when we actually name these guys, as we talked about, we do use ENE for double bond or YNE for triple bond. There is an additional thing that we do with double bonds and triple bonds that we don't really do with single bonds. And that is we actually give the double bond or the triple bond the priority in terms of numbering. And when there is a difference, which is about 4 or more carbons, where that double bond or triple bond could be located, we also need to give the location of where you can find that double bond or triple bond. Everybody else is sort of works the same way. So since we have these here, let's kind of go through a little bit of the naming here, which is we still want to find the longest continuous carbon chain. The deal though is if it is a double bond or triple bond, it has to be part of the longest carbon chain. So you can't go around the double bond or triple bond. It has to be part of that longest carbon chain. So if we look at this one, clearly 1, 2, 3, 4, 5, 6, 7, and 8 in this case. So 8 carbons is based off of octane, but since this has a double bond, it's not going to be octane, it's going to be octene, ENE. So as I mentioned before, everything comes back to those first 10 alkane names. So it's really important, as I mentioned earlier, to get a handle on this. Now, we actually have to give the numbering priority to the double bond, which means we have 2 ways of numbering it. 1, 2, 3, 4, 5, 6, 7, or 8. The other way that we can number it is obviously in the other direction. And we're going to go 1, 2, 3, 4, 5, 6, 7, and 8. Just like anything else in organic chemistry, we're always looking for the smallest numbers. So going in the blue direction, my double bond starts at carbon number 3. Going in the red direction, it starts at carbon number 5. So we would want to go in this direction since it gives the double bond the smaller number. And we will have to add a little bit of a 3-octene to it. The 3 is the location of the double bond. So that is the location of the double bond. Now, once you sort of lock in whichever way you are numbering based on the double bond or triple bond, any other groups that are attached has to be numbered the same way. So that's your priority is the double bond or triple bond. And whichever way you lock in for that numbering, if there's anything else attached, gets numbered the same way. Why don't you try naming this one? How many carbons here is our longest carbon chain that contains the triple bond here? So what do we think? What's the longest carbon chain here that has the triple bond? 7, 8. So let's see. So again, there is one here, right? And we don't want to forget the one on the other side. So that is 2, right? 3, 4. You could go down 5, 6, and 7. So that's 7. Now the other option obviously would be just to go straight across, I think. So 1, 2, 3, 4, 5, 6, 7, and 8. So it does look like 8 is going to be our longest carbon chain here. That again is going to be based off of octane. Since it has a triple bond, we get rid of the ANE and put YNE, octine here. Now we need to give the location of the triple bond, which hopefully you can see just right off the bat there should probably be carbon number 1, right? Since it's sitting right there. So this is a 1-octine because of the location of the triple bond. But we do actually have a group that's down here, right? And we actually have a 3-carbon group that's hanging out there. And 3 carbons is based off of propane. And since that is a propyl group, right? Lastly, here we need to give the location. So since we locked this guy into being carbon number 1, this would be carbon number 2. That would have to be carbon number 3. And that means that our propyl group would have to be carbon number 4. Just like everything else we did, this is going to be 4-propyl dash 1-octine. Yeah. So again, kind of works the same way as alkanes. The additional thing is we shift the priority to double bond or triple bond in terms of the numbering. By the way, if there happens to be a tie, and it can happen, double bond or triple bond, a tie regardless of which way you go, next important thing is groups in alphabetical, and whichever way gives those guys the smaller number to the more alphabetical sort of ordered one. So it is possible definitely to end up with sort of a group. Now, by the way, the one we saw earlier, which was ethene, there frankly is only one place to lay up that double bond, so you do not have to give a number. And so again, around probably 4 or so carbons is where you start to see you got to kind of need to start to put some ones as well. Because technically speaking, and sometimes people will put a number with this one, but if I put it here, that technically would be carbon 1, right? And if I put it over here, this then would be carbon number 1. So technically it's sort of the same. Although I've seen people sometimes put numbers with that one, but definitely we're starting about 4, so you got to definitely lay up some numbers for that double or triple bond. Any questions there? Yeah. So as we've been talking about, as we just saw there, again, ENE for double bonds, YNE for triple, and we're going to give the location of the double or triple bond, and everybody else gets numbered accordingly. All right, so why don't you try these? Why don't you give these guys a name? Why don't you also maybe draw a couple here? So let's see, maybe I have to find something to draw. Okay, so since we're getting to the end, let's take a look and see here. So we'll start on the left there. Again, pretty much all organic name is the same, longest continuous carbon chain. Again, pretty much it just needs to make sure it contains the functional group. So in this case, our functional group is a double bonded carbon. So we'll go 1, 2, 3, 4, and 5. You could also get 5 going downward if you want as well. But in this case, I'm just going to go straight across since they both give us the 5. So once again, our longest continuous carbon chain is 5. That once again is based off of pentane. Here we do see obviously our double bond, which means no longer ANE, now going to be pentene here. We do need to give the location of where that double bond is because it's definitely more than 4. And we want to give it the smallest number. So if we start numbering left to right here, get some of that there maybe. If we go left to right, we would go 1, 2, 3, 4, 5. If we go in the other direction, kind of right to left here, we would go 1, 2, 3, 4, 5. So again, remember that once we have a double bond or triple bond, it does take the priority in terms of numbering. So although the group has a smaller number going in the blue direction, it is really the black direction here that gives our double bond the smaller number of 2, and that is the direction we want to go. So again, once we sort of lock it into going left to right here, the groups now are numbered accordingly as well. So we definitely would not use this numbering at this point. But we are going to use the left to right numbering. That means that our double bond would be at 2-pentene. Again, the location of where we can find our double bond. And because of that, we now see that our only group that's here, which is a lonely line, which is a methyl group, right? Because there's nothing written at the end of the line, should be a carbon number 4. And we pop that in there with our appropriate kind of dashes, if you will. And we end up with 4-methyl 2-pentene. Any questions on the name there? All right, looking at the bottom one here, we definitely can see a triple bond as we talked about. The geometry of that now kind of flattens out. So again, sometimes you will see it. I'm okay, by the way, if you want to draw it, not showing the geometry and just want to put the lines, I'm good with it. But in books and stuff, sometimes you will kind of see it again, kind of flatten out. So we want to count here. We got 1. We again don't want to miss the one there, which is 2. Don't want to miss the one on the other side, which is 3. 4, 5, and 6. That looks like 6 carbons in a row and nothing else there, basically. So that's going to be based off of hexane. Because we have a triple bond, that goes away and it now becomes hexyne, YNE at the end. We do need to give the location. You could probably just see looking at it. If you go kind of right to left there, you're going to hit the triple bond at carbon number 2, and that would be 2-hexyne. Any questions on those names there? All right, so drawing, we're going to work backwards like normal. And when we take our look backwards, I see ENE, which automatically should tell me it is a double bond somewhere in there. And pentane basically means 5. So just like we did previously, we're just going to start with the 5 carbons. And now because of the ENE, I know that that double bond is going to be at carbon number 2. So you still have the choice of left or right. Again, I'm going to start with my carbon number 1 being there, which means my double bond would be at carbon number 2, which would be right about there. That takes care of that. And now since I did start at carbon number 1 here, my carbon number 4 would be down here and go below so I don't run out of room. And I'll put my ethyl group in there, and that will take care of that. Once again, just like before, everything else is just hydrogens. So this one here has 1 line, needs 3. This has 3 lines, only needs 1. 3 lines only needs 1. 3 lines only needs 1, and 3 hydrogens here. Again, this would be your condensed formula. If you're going to do line structure, still works the same way. We'll start with 5 carbons, 1, 2, 3, 4, and 5. Again, I'm going to call this carbon number 1. So my double bond is going to be at carbon number 2, which would be right about there. And that's carbon 1, 2, 3. And then my 4th bond would be here, which is, what is this case? Ethyl. In this case, so do a little bit of something like that. Yeah. Other questions on that there? Lastly, we take a look backwards here. I see YNE. That means I should lay myself up a triple bond somewhere, right? And hex is from like hexane, which is 6. So we're going to go 6 carbons on this one. 1, 2, 3, 4, 5, and 6. Again, I'm going to call this carbon number 1, which is actually where I'm going to put my triple bond. And that would take care of that part of the name. Since once again, I called this carbon number 1, for me, my 4th carbon would be down this way, which has a methyl group on it. You could also go upwards with the methyl group. It doesn't matter. Again, you could go up or down on that. And then my 3rd carbon, which would be here, I'm going to go down because I'm running out of room going up. So we'll go there. And again, the last thing to fill in is going to be our hydrogens. We would need 1 hydrogen there. We would need actually no hydrogens there. We would need 1 hydrogen there. We would need 1 there, and 2 and 3. And once again, if we were going to do some lines, same deal. You're just going to go 1, 2, 3, 4, 5, and 6. Triple bond, like I said, you could do it like that without straightening out. I'm all good with it. And we'll go carbon number 3, 1, 2, 3, bromine. And carbon number 4, methyl. Yeah, it looks something like that. Any questions on naming, drawing? Not too bad. All right, we'll lay it up.